to the cloud. So a little zoomage. Profit a company makes on producing X, Y, and Z 1,000 units of products is given by function. If manufacturing constraints force x squared plus 4y squared plus 2z squared to be less than or equal to 8,000, find the production parameters for maximum profit for the company. All right, so really it's, going back to everything, it's commonplace when you're dealing with calculus. We're almost always talking about maximizing, minimizing, but you almost always we figure out a way to work in profit and revenue and cost and things like that. So that's where we're at this point. All right, so we have our P of X, Y, Z. I'll make a little note of that. It's as simple as it gets for a multivariable function. Kind of nice. So when I go to find my partials, P sub X, P sub Y, P sub Z, is going to be 4, 8, and 6 respectively. All right, so that part's not too bad. Then the other component is the constraint function, x squared plus 4y squared plus 2z squared is less than or equal to 800. But it, just like we talked about with the conic sections, yeah, it was definitely last class. We talked about that. It really was with the idea that there's a boundary in there somewhere. It's not so much a matter of saying, well, this is an inequality and you just got to live with it. It's really a matter of saying that you have an inequality, yeah, but all that is the coloring inside or the shading inside of some boundary. It turns out that this is a sphere, but it's a filled in sphere. So everything within the surface area of that sphere is going to be accounted for, right? So we can't go beyond that outer edge. So that gives us x squared plus 4y squared plus 2z squared equals 800 as our outer bound or set of boundaries. All right, so if I solve this for 0, essentially just subtracting an 800 from both sides, that gives me my g function, which I'm going to call g of x, y, z in this case, because it's a function of 3 variables. All right, so I now know that g of x, y, z is equal to x squared plus 4y squared plus 2z squared minus 800. All right, I'm going to just smidge this over a little bit. So I could figure out my partials from there. All right, it shouldn't be too bad. So my partial derivatives, g sub x, just a clean 2x, g sub y, a clean 8y, and g sub z, a clean 4z. The 800, the negative 800 is constant, so that's going to go to 0. All right, so what we get from the Lagrange multiplier concept is that each set of partials will be equal to one another in a proportional relationship based off of some proportionality constant known as lambda. So I could say that P sub x is equal to lambda times g sub x. P sub y is equal to lambda times g sub y. And P sub z is equal to lambda times g sub z. All right, computationally, it's not bad. 4 equals lambda times 2x. 8 is equal to lambda times 8y. And 6 is equal to lambda times 4z. All right. So like I said, as computations go, it could be a whole lot worse. So not too bad. Not too shabby. All right, but we got to do something with this. All right. The issue that we're running into is that, you know, in the last problem, and if you had a chance to look at the video, or even if you followed along with my lesson from last class, even the fact that it didn't work out, you still kind of gained something from it, in that there was a way that you could solve the expression or the equations in order to get a nice substitution that allows you to make some clean cancellations. But it doesn't seem to be the case here, because there's no instance in which we're able to cleanly just cancel out a variable. All right, so we're kind of stuck with them. Best we could do is cancel out some constants. All right, but what we can do is solve for lambda. All right, so in each case. All right, or I mean, we could solve for lambda, but really, if you think about that, that would allow us to set each of these expressions equal to one another, and then we'd have an equation that has x, y, and z in it. So maybe that's not the best way to go. Best way to go, it seems, would be to solve for x, y, and z, because I'm just going to go back to, well, it really doesn't matter which relationship we use, but anything from this block over here of equations has a relationship between x, y, and z. So if I solve each of those equations for x, y, and z, or x, you know, respectively, x for the first one, y for the second one, z for the third one, then I can substitute it into that constraint function, and I'll get a single equation in terms of the one variable lambda. Right, so that seems to be the best recipe. So divide both sides by 2 lambda here. Oh, that's good. That's the line draw tool. So 2 lambda. So we're looking at x equals, looks like a 2 over lambda. This one's a lot easier, you know, dividing by 8 lambda. So y is going to be equal to 1 over lambda. I think I just said a lot easier. It's just a little easier. It's basic algebra. And then dividing by 4 lambda. I almost wrote a z. For quality lambda. I try to make my lambdas look halfway decent, because if you've tried making those lambdas yourself, see that they're very easy to kind of mistake for x's. If you kind of extend that one little stem a little too far, all of a sudden you got something that might confuse you and make, you know, you think it's an x and it really isn't. All right, so I'm going to snag, it really doesn't matter. I'm going to take x squared plus 4y squared plus 2z squared equals 800. I'll just grab that one. All right, make a nice substitution. This is going in for x. This is going in for y. And this is going in for z. All right, so 2 over lambda squared plus 4 times 1 over lambda squared plus 2 times 3 over 2 lambda squared is going to be equal to 800. Simplify. 4 over lambda squared. Yeah, looking 2x like. Plus, this one's also going to be 4 over lambda squared. Plus, we're going to get 9 times 2, so 18 over 4 lambda squared, but then that's going to be 9 over 2 lambda squared. is equal to 800. All right. So then, you know, you get a fractional equation. Technique that I could use here would be to, oh, wrong screen. Technique I can use here would be to multiply through with a 2 lambda squared. Clears things up a little bit. I can combine like terms too if I want. Really doesn't matter. You know, at this point, it's just algebra. Honestly, if you want, you can solve it like really any way you want. You could use Desmos if you want. It's just a lot to type in. You know, let's give it a look though, because if I combine these terms, we're gonna have 8 over lambda squared plus 9 over 2 lambda squared is equal to 800. It's going to be a little easier to type in. You know, maybe you don't want to do it this way. That's fine. Now I'm actually going to put it in as an X. In the algebra, I want to preface all this by saying the algebra here is not, for this problem, is not difficult. I just want to kind of remind you that this is still on the table. I mentioned it last time, but that doesn't mean that people, I don't want to say listen, because that kind of seems rude, but I'll say absorb what I say the first time around. All right. So if I'm looking for a solution to an equation, you might remember this from TI calculators. One thing that you could do is set them up as 2 separate equations. Y equals. All right. In this case, you're looking at a constant function. Now it's 800 units up, so it's not the most user-friendly thing in the world, but I can make my y-axis go to like 1,000 and see if there's an I think I put 100 in there. I did. Look for that intersection or those intersections, and Desmos does a really nice job of highlighting those intersections for you. So we get, just by doing the workout this way, some clean intersection values, 0.125. And if you don't know what those are, what that value is in fraction form, you can put it in as 1/8. So you can get it that way. You know, lambda is going to be plus or minus 1/8. All right, just by using the Desmos calculator. All right, but like I said, the algebra here is not difficult because I would just get a common denominator, so top and bottom by 2. All right, so this would be 16 over 2, which would correspond to 25 over 2 lambda squared. I'll just kind of chuck this off on the side. Is equal to 800. So we'd have 1600 lambda squared is equal to 25. Lambda squared is equal to, well, I would imagine 1 over 64. Just double check that. Which would in turn give you the lambda is equal to plus or minus 1/8. All right, so we got the appropriate lambda values, which is great. Look at all this work. And it all started off with a pretty simple set of partial derivatives. It's just the algebra that took us down a road, right? But in reality, the algebra wasn't really the difficult part. And also, this really doesn't take up a whole page. I'm just writing like huge like here. So it's time to shrink it up a little bit. Make it all fit a little bit better. From this, now I have some lambda values. I can determine what the corresponding x, y, and z values are. All right, so I'm going to have a couple of sets, and you can organize it any way you want, as long as it's reasonable. So x is equal to 2 over lambda. Well, if I'm focusing on the 1/8, right, that's one possibility, right? Because remember, it's plus or minus. So we have the 1/8. I'll do negative 1/8 first, actually. Smallest to largest. All right. 2 divided by negative 1/8 is going to be negative 16 or positive 16. We'll keep change flip action. And we have 1 over lambda is the y. So negative 8 or positive 8. And then the last one, that's the weirder one. You know, maybe you do the work a little bit on the side, but you're really looking at taking negative, 3/2, and you're multiplying the 2 by the negative 1/8. So it's really 3 over negative 1/4. All right. So 3 over negative 1/4, keep change flip, is going to be negative 12. So 3 over 2 lambda, negative 12, and you know the other possibility would be positive 12. Confidence check here. You know, best laid plans, you try to do things in your head and things go south pretty quickly, as you've seen happen to me repeatedly. All right, so it's asking for the production parameters for this manufacturing scenario. X, Y, and Z represent thousands of units of products. So with that in mind, you know, going into the problem, I'm like, I don't know. It could be positive or negative, but it kind of makes sense that we would toss the negatives now, because we're not going to produce negative products. Although, you know, you don't want to toss the negatives out of hand just because they're negatives, as you know, even when it comes to stuff like products, because it could be, you know, products promised. You know, you're short 16,000 products, 16,000 of X, 8,000 of Y, and 12,000 of Z. All right. So you don't want to just say, oh, it's negative, it's gone. You know, you really want to think about it. But when you consider this scenario, it seems like they're calling for positive values. Find the production parameters for the maximum profit for the company. Right? So it seems like, well, if one of them could have possibly have been a minimum, then I would hope that it would be the one that we just got rid of. And you know, that's just generally how these questions work out, where the problem is designed to give you kind of what you're looking for. There are ways to test, but you know, it's kind of a different conversation for a different moment. So we're going with 16,000 of X, 8,000 of Y, because they never really defined what these things are, these variables we're representing, and 12,000 of Z. All right, so a whole lot of writing, but you get there. Now, pretty safe to say that if that kind of question ended up being a multiple choice question on a test, that would be the mother of all gifts. You know, like that would be like an early holiday present, because of all the work that you'd be avoiding. Although you kind of look at it and say, well, maybe it's not, because I did all the work and I just guessed the wrong choice, and you know, that could be a different story. But yeah, saving you the work would be a nice treat. But I would not, let's just put it this way, I would not count on this kind of question being a multiple choice one. All right, so let me stop that recording so you have